this is Unit 4, Lesson 4. We're going to start looking at complex and imaginary numbers today. All right, so let's start by taking a look at this Venn diagram that kind of just helps us organize numbers. Now, everything in this realm right here that I'm circling in blue is the different sets and subsets of numbers that you have learned so far. Up until now, all numbers have been real. All right, what does that mean? That means that you're not taking a square root of a negative number. And that's the difference that will get us into the imaginaries. We'll talk about that in a second. So real numbers can then be broken down into two groups, either rational or irrational. I think of they're either crazy or they're sane. You can't be both, it's one or the other. So remember that irrational numbers are numbers that cannot be written as a fraction. So they are non-terminating and non-repeating decimals. So they're decimals that go on forever and ever and ever, and there is no pattern. Your most common irrational number is pi, and then really any square root of a number that's not a perfect square ends up being irrational. Your rational numbers are your numbers that can be written as a fraction. So in terms of decimals, they're terminated, meaning they have an end to them, like this decimal right here of 0.75 can be written as 3/4, or there's a pattern. So like if I divided 1/3, you get 0.3 repeating. That can be 0.3 repeating can be written as a fraction, as 1/3, so that is rational. And then from there, your rational numbers break down in a couple smaller subsets, sets that we remember or have learned before. Now, what we're adding here in this new piece is our pure imaginaries and our complex numbers. So it's important to realize that all numbers are classified as complex numbers. And we're not changing what you've already learned, we're just expanding upon it. A complex number can be written in the form as a plus bi. A is your real piece, and your BI is your imaginary. All right, so even a number like 5 can be written as a complex number. The real part is 5, and there's 0 imaginary pieces to it because there's no square root of a negative. Now, we don't write numbers like that because 5 plus 0 anything is just 5. Sorry, I had to take a drink. But it's important to know that any number can be written in a plus bi. All right, now, so the new piece over here, pure imaginaries, are numbers that only have an imaginary piece. So they are square roots of negative numbers. Okay, so the square root of -5 would be written as 5i, and we're going to get into how I know that in a moment. Or I could have -3i, and this is how I could write an imaginary as a complex number. There's 0 real parts to it, and in that example, 2 imaginary parts, and we'll get into that momentarily. So just a reminder, whoops, your different sets, what they are, any symbols for them. Okay, so let's start talking about what is I and all that good stuff. So in math, we say the letter I is defined as the imaginary unit. So I stands for the square root of -1, okay? So if I is the square root of -1, we want to figure out what is I squared equal to? What is I cubed, etc., etc. So let's start by taking a look at our patterns. We can use these patterns to help us simplify radical expressions, which we'll get to shortly. So first we need to simplify and then add, subtract, multiply, or divide. We'll get to that. So let's figure out our patterns for I. So you need to know I is equal to the square root of -1. Now we can never leave a negative under a radical, so we use this symbol instead, I. Okay, well if the square root of -1 is I squared would be what? So that's saying I have the square root of -1 squared, or you could write that as the square root of -1 times the square root of -1. But when all is said and done, if I'm squaring something under radical, remember the square root and the exponent kind of just cancel each other out. So the square root of -1 times the square root of -1 ends up just being -1. So I squared simplifies to -1. All right, so for I cubed, I have the square root of -1 3 times. Okay, or I can think of the square root of -1 times the square root of -1 times the square root of -1. Okay, well the square root of -1 times the square root of -1 we just did. I have -1 times the square root of -1. All right, so what does that give me? That gives me negative square root of -1. Oh, can't write that. We replace this with an I, so it's -I. All right, I to the 4th. I've got 4 of them now. All right, you want to start looking for patterns too. So I got the square root of -1 4 times. Okay, or I can write that as the square root of -1 times the square root of -1 times the square root of -1 times the square root of -1. Okay, well, the square root of -1 times the square root of -1 was -1. Same thing over here. And -1 times -1 gave me 1. All right, let's take a look at I to the 5th, and we're going to start seeing a pattern, okay? So I to the 5th, I can write that out 5 times, but kind of to save room and to kind of think of a shortcut, let me break this down. I to the 5th is the same thing as I to the 4th times I, right? I'm just breaking it up into two different exponents. Okay, why am I using those exponents and not like I squared and I cubed? Because we know I to the 4th is just 1. So if I can pull out a factor of 1, I've now got 1 times I, which is just I. So I to the 5th simplifies to I. I can do the same thing with my I squared. I've got I to the 4th times I squared. Sorry, I meant I to the 6th. All right, so I've got 1 times -1 because I already know I squared simplifies to -1. So that means I sixth is -1 as well. For my I to the 7th, I've got I to the 4th times I cubed, right? Because 4 plus 3 is 7, so I'm just breaking it up into things I already know, making it easier. So that means I have 1 times -I, because I already know I cubed is -I. Therefore, this is -I. I to the 8th is I to the 4th times I to the 4th, 1 times 1, which is 1. So if you notice, I is a repeating pattern. It repeats in groups of 4. So really, you just need to know I squared, I cubed, and I to the 4th, and you can simplify any power of I. All right, if I go down here, so let's take a look. I to the 25th. We want to pull out as many groups of 4 as we can. So if I break this up, I know that I to the 25th, I can do I to the 24th times I. Why 24? Because that's the biggest number that can be divisible by 4 within 25. And I'm left with the remainder. Well, no matter how many groups of 4, there's 6 of them to be exact, but it doesn't matter. No matter how many I to the 4ths I have 1 times 1 times 1, whatever, it just gives me 1. So really, all I really need to look at is my remainder, and that tells me if it's a power of 1, 2, 3, or 4, and then I can simplify from there. All right, so this really just ends up being I. If I look over here at 39, I want to figure out the biggest whole number that I can divide evenly by 4, which is 36. So I've got 36 and 3. Okay, well, 36 is 9 divided by 4, which is, no matter what, will be 1. So really, I'm looking at an I cubed. And I remember from earlier that that simplifies to -I. Okay, so you're really just looking for that remainder, and if your remainder is an exponent bigger than 4, then you didn't pull out enough groups of 4. There's still more that can be done in there. So this is going to help us as we are simplifying. So we're kind of going back to what we did last unit with simplifying radicals, multiplying, dividing, adding, subtracting, and all that good stuff, but now we're going to deal with negatives under the radical. So a few rules for us to follow. All right, never leave a negative under a radical. Okay. If you have a negative under radical, there's still an I in there that you can take out. Never leave an I with an exponent. Any I that has an exponent bigger than 1 is not simplified yet. You can go through and simplify that. Don't leave a radical in the denominator. Okay, that's not a new rule for us. We know that one. Never leave an I in the denominator, because remember, I is the square root of -1. So technically, if you have an I down there, you still have a radical, which is a no-no. And then just follow your rules for simplifying radicals. All right, so in all the examples, there's one done for you. I'm going to go through the simplifying on the right side for you. Okay, so in this first one, we've got 12 times the square root of -1, which is also just known as I times the square root of 12. So you can write it like this, or you can just realize, hey, that's an I. So first thing is first, you've got to pull out your I. Take your I out. Always take out that negative before you do anything. Before multiplying or simplifying, you must take that I out. All right, now we can go ahead and simplify and break that down. So I broke that down into 2 and 6, 2 and 3. We've got a group of 2. Bring this to the outside, which is how I got 2I radical 3. All right, go ahead and pause the video. And I'm going to do the you try for you, and I want you to do the you try as well, and then press play to check it. Pause the video. All right, and I got 3i radical 6. Started by taking my negative out, so pulling an I to the outside, and then I broke down the 54. You can pause and look through my work if you need to. All right, I'm going to move on to example number 3. So in this one, it's the same thing, but now I have variables underneath. But first things first, take out that I. Okay, so I've got 3i times the square root of 50x cubed. And now from here, I simplify it like I normally do. 2 and 25. All right, and whichever way you want to show your work is fine. 5 and 5. I've got 3 x's. Here's a group. Here's a group. So on the outside, I'm going to do the 5 times the 3 that's already there, which is 15. And I usually like to keep my variables in alphabetical order, so I have ix. I is just a letter, guys. I mean, it's a letter, it's a variable with meaning, but treat it like a variable, okay? So I is on the outside, and x from over here, which leaves me with 2 and this x underneath. All right, so same thing, pull out the I, treat it like you normally would. Go ahead, pause the video, and do the you try on your own. All right, and you can see that I went ahead and simplified, took my I out, broke down the 98 and the x to the 5th. All right, and you can see my work from there. All right, example number 4 is now multiplication. So if you think back to our rules for radicals, for multiplication, we can multiply our coefficients, multiply our radicands, and then simplify. Before you do anything, you need to take that I out. It will make a huge difference if you don't. Okay, I cannot just simplify numbers under a radical when there's a negative. So I first need to deal with my I. So over here, I've got the 3i square roots of 27 times 4i radical 21. And then from here, I could simplify the radicals, combine them, and then simplify, or I can just combine them and then whatever. All right, but if I do that, I've got 12i squared times the square root of 27 times 21. Hold on. 567. And when I break that down, I can break it into 3 and 189, 3 and 63, 9 and 7, 3 and 3. All right, so I've got a group here, a group here. Okay, 3 times 3 gives me 9. Sorry, I'm just looking at my work up above. Feel like, oh, sorry guys. This 3, I was looking at the wrong line. There is no 3 there. All right, let me rewrite this problem. Can't go back and cut that out. Pause, please. Here we go. I'm sorry. Whew. There is no 3 there. So that's just I square root of 27 times 4i square root of 21. You're probably like, where did that come from? I made it up. All right. So we had 3 and 189. We had 3 and 63, which gave me 9 and 7, because I know that's a perfect square. 3 times 3 is 9, times the 4 that's out there is 36. We'll deal with the I squared in a second. And then I had a 7 left underneath. Now remember, one of the rules is you cannot have a variable with an exponent, or you can have an I with an exponent greater than 1. So think back to those 4 things. I squared was the same thing as -1. So this is 36 times -1. So this would be the correct answer. Okay, you cannot leave. You're not done if you have an I that has an exponent bigger than 1. All right, pause the video, try the next one on your own. All right, here's my answer. Okay, when I multiplied, I ended up, sorry, it's 144 squared to 15. Oh, that was weird. When I multiplied, I ended up with -12i squared radical 2,160. I broke that down. There, it's divisible by 144, which is a perfect square. So then I moved that, took the square root of this, got me 12. So -12 times that 12, -144i squared. I squared is -1, which is how it ended up as a positive 144. All right, you can pause and take a look if you need to. All right, example number 5. Now we're talking division. The same rules apply. Cannot have a radical in the denominator, but I still need to rationalize my numerator first. So it's easier to kind of break them up, and I end up with I times the square root of 8 over the square root of 5. All right, because my I was next to my 8. Now I can either simplify and then rationalize, or rationalize and simplify. It's up to you, but the same rules apply for rationalizing. Since it's monomial, I'm just multiplying both by the square root of 5. So I have I radical 40 over 5. This can be reduced. I have a factor of 4 in there. So I get, I can pull out 2. So 2I square root of 10 over 5. Right, because 40 breaks down into 2 and 20, 2 and 10, 2 and 5. So 2 radical 10. And nothing can be reduced. All right, go ahead, try the next one. Pause the video. All right, 2I radical 21 over 7. Pulled my I out, rationalized my denominator. All right, let's pop over to adding and subtracting. Okay, so our adding and subtracting is just like before. You can only combine things that have identical variables. So we're going to treat our I just like a variable. It just is a variable that has a purpose. So in my first example, I started by distributing my negative, giving me negative 5 plus 3I, and then I combined my like terms. Now we want to write our answer in A plus BI form. So my real piece first and then my imaginary piece. All right, in the second example, in example 7, I had to distribute a 3I, giving me 18I minus 15I squared. Okay, can combine like terms, so my 2I and 18I combine to 20I. And then I couldn't keep this I squared because it has an exponent bigger than 1. So negative 15 times negative 1, because that's what it simplifies to. All right, so I combined my like terms and ended up in A plus BI form. So guys, I'm treating it just like if I'm doing X's or B's or whatever letter you want to use. The only difference is at the end, I cannot keep anything with an exponent greater than 1 when I'm dealing with I's. So I need to simplify from there. All right, try the next 2 problems. I'm going to pause the video. Try those 2 you tries on your own. All right, and take a look in the first one. I distributed a negative through, combined my like terms, and I was left with negative 5 minus 7I. All right, in my second one, I distributed 5I cubed, which gave me 10I cubed minus 15I to the 4th. I cubed is the same thing as negative I to the 4th is the same as positive 1. So I ended up with 3 minus 5I minus 10I minus 15. So I combined my like terms and got negative 12 minus 15I. All right, multiplication, same things apply. Multiply, change your exponents, simplify it. So you don't need to use a box unless you want to. You can just FOIL it out. 15 times 2 is 30. 15 times negative 4I is negative 60I. 3I, 6I, minus 12I squared. So here I have 30 minus 54I minus 12 times negative 1, because that's what I squared is. So that gives me a positive 12, so that's how I ended up with 42 minus 54I. It's the same stuff, guys. All right, the you try over here, please just be careful. That is a binomial squared, so it's 3 minus 2I times 3 minus 2I. Go ahead, pause, and try it on your own. All right, and you can see what I did there when I FOILed it out. Leave me with 9 minus 12I plus 4I squared, which then simplified, and I ended up with 5 minus 12I. All right, so conjugates, same rule applies, whether I have a variable, a radical, whatever. A conjugate is when you have 2 binomials when your sign in the middle is opposite. So the conjugate of 3 minus 5I is 3 plus 5I. The conjugate of 4 plus I is 4 minus I. All right, so what is our conjugate of negative 7 plus 3I? That's right, it's negative 7 minus 3I. So let's take a look together. What happens when I multiply conjugates here? We know with radicals, the radicals cancel out. So what do you think is going to happen? I feel like this is a Blue's Clues episode where I just wait for you all to shout to the TV screen. All right, so let's multiply it out. So 2 times 2 is 4 minus 6I plus 6I, key phrase there, opposite signs, minus 9I squared. So those cancel, and I'm left with 4 minus 9 times a negative 1, or 4 plus 9, which is 13. So what should we expect to happen? Every time, the result is always what classification number? A real number. I mean, you can technically write complex, but no, to break it down even farther, to be more specific, you're going to get a real number. Your imaginary pieces disappear. Okay, and we can, Now, we can't say for sure it will always be a natural or counting. It could be a negative number. So real is where we're going with that. All right, last little bit to finish up. So dividing binomials. So same rules apply, guys. No, you need to rationalize your denominator. No radicals in the denominator. So remember, the conjugate is a minus bi. If there's a binomial, you have to multiply by the entire conjugate. You can't just piecemeal it. Okay, so for example, this one, when I'm given this problem, I have an I in my denominator, which is bad because that really means there's a radical down there. So I need to multiply both pieces by 4 plus 2i. All right, so in my numerator, okay, we've got to do a little bit of work, so I'm going to give myself a little bit more room. So my numerator ends up being 20 plus 10i plus 4i plus 2i squared. So I've got 20 plus 14i plus 2 times negative 1, also known as negative 2. So I've got 18 plus 14i. Okay, let's leave that for now and then come back to see what can be done to simplify, if anything, later. I know my denominator, my negative should cancel out. So 4 times 4 is 16. 4 plus 2i, those two should cancel. So I've got negative 4i squared, which is also positive 4, right? Because 16, negative 4 times negative 1. So that should be 20, 16 plus 4. And I can reduce. How? I can divide them everything by 2. Make sure I can divide into both pieces. So I have 9 plus 7i over 10, or 9 tenths plus 7i tenths. Sometimes you see it broken up, but you can write it as one fraction. All right, good. Pause the video. Try the next one on your own. All right, I end up with 7 minus 17i over 26. Or 726 minus 17i 26. Okay, can't reduce anything there, so I'm done. All right, we are done with the video.